Welcome to Theory of Computation. This is lecture number 42. In the last lecture, we proved that generalized geography was p-space complete. So far, we know three problems that are p-space complete. One is the quantified Boolean formulas, the other one was formula game, and the third one was generalized geography. We said that we'll finish the study of p-space complete problems over here, and what you can do is you can search on the internet for other interesting p-space complete problems. The theory of p-space complete problems is also very rich, and the class p-space complete problems contains a lot of interesting problems. However, what we did was we noticed that p-space is an extremely large class of problems, and we know that p is contained in np, and np is contained in p-space. And it's widely suspected, it's widely conjectured that these three classes are separate classes, that all these containments are proper. So this means that there are problems in NP which are not in P. And the best candidates for such problems are, of course, NP-complete problems. Similarly, it's conjectured that there are problems in P-space which are not in the class NP. And P-space complete problems are the best candidates to be such problems. However, we don't even know if P is properly contained in P-space. That remains a very open conjecture, and no one has been able to resolve it. It would be very exciting if someone were able to separate these two classes, if someone were able to show that there are problems that require polynomial space but cannot be solved in polynomial time. We have no idea how to prove such a claim. The techniques developed in computer science so far have all failed to resolve this question. As we noticed before, that P is what we consider to be, well, P stands for polynomial time, but you can also think of P as standing for practical. These are the problems that we can solve practically, that require polynomial time. So these are problems that you expect that you would be able to solve on your PC in reasonable amount of time. And the boundary between P and problems which cannot be solved in polynomial time is what we are trying to understand. And the class NP is actually an attempt to understand what happens when problems become very complex. What is it that causes problems' complexity to become so high that they cease to be practical? And NP-complete problems are very nice examples, candidates for which show us what essentially happens to a problem, what essentially are the ingredients that go into a problem so that it will have a high complexity. P-space complete problems are even harder. Now, if we think from a practical point of view, we have sort of gone off on a tangent. Somebody who's extremely practical would say, well, we can't even find polynomial time algorithms for NP-complete problems, and you're studying problems which are even harder than this. And this seems like an exercise in futility. The interesting thing to study would be to study practical problems. So it would be very interesting to study subclasses of the class P. And since we know that these problems can be solved in practical amount of time, in polynomial time, we can ask questions which are very interesting. We can ask questions, how can we reduce the space requirement of such problems, which we know how to solve practically. And if we get answers, these answers will have very real applications. These answers will have very real consequences on problems that we solve every day. What we will do now is define two complexity classes that are inside P and study them from a complexity theoretic point of view. We would also define complete problems, and for this what we will do is once again take our inspiration from the theory of NP completeness. In order for us to define these two complexity classes, what we will have to do is redefine the notion of reducibilities. It will turn out that to study the questions that we are interested in, polynomial time reducibility is not going to be enough. Once again, both these classes are going to be space complexity classes, and they are going to once again compare determinism versus non-determinism. Let's begin. Let us define two new complexity classes. Let's define L to be space of log n and NL to be non-deterministic space of log n. These two complexity classes turn out to be very interesting. Let's think about the class L first. Well, I should be calling this class log space, and sometimes it's called log space, but this is the set of all problems that we can solve in logarithmic space. And once again here, remember the model of computation that we have, that we keep in mind. Space, when we measure space, we think of a Turing machine which is given an input. It's allowed to read the input over and over again without ever changing the input. Then this machine also has an output device, and it produces the output, and the machine can only write on this tape. It cannot read things off this tape, and whenever it writes, it keeps moving forward. Then the machine has a work tape. The machine can write any symbol it wants on the work tape, and only the space that it uses on the work tape is what is considered to be the space used by this Turing machine. A very nice model that you can keep in your mind is, think of a computer which has a CD-ROM. So the input is being provided to the computer on a CD-ROM, and this computer has no screen. Let's say this computer just has a printer, and the machine, what it does is it reads something off the CD and then it prints something on the printer. So it cannot read off symbols that it's printed. However, the machine uses internal memory, and that's what models the work tape. So the space that is calculated is the amount of space used on the work tape. Neither the input nor the output counts towards any space used by the machine. So L is the class, or log space is the class of all problems that we can solve using logarithmic amount of space. Similarly, NL is the set of all problems that we can solve using logarithmic amount of space by non-deterministic Turing machines. So there we allow ourselves non-determinism. Notice that we can count up to the integer n using a log n bit counter. Thus, you should think of L as the set of all problems that can be solved using a fixed number of counters. NL, of course, is the non-deterministic analog of this class. And this thing you should keep in mind. If somebody tells you that you are supposed to design a logarithmic space Turing machine, this essentially means that you are somehow supposed to compute something using only counters, and these counters cannot be very large. However, this is not the formal definition. This is only an intuitive understanding of the class L. Formally, the class L is the set of all problems that can be solved in logarithmic space, and that logarithmic space may not be storing counters. It may be storing some other information if the algorithm is designed that way. So we have two classes. One is called L, which is logarithmic space. The other is called NL, non-deterministic logarithmic space. And what we want to do is see what does non-determinism do to these two complexity classes. Remember that we had Savage's theorem. Savage's theorem actually helped us resolve a very interesting space complexity question. We said there's the class P space and there's the class NP space. And Savage's theorem said that both these classes are the same. Thus, non-determinism, when we are talking about polynomial space, does not buy us anything extra. Whatever can be solved in non-deterministic polynomial space can also be solved in deterministic polynomial space. Now, we go down inside P and define these two classes, and we want to ask similar kind of questions. What we know is that L is contained in NL, which is contained in P, which is to say that L and NL are subclasses of the class P. Well, why is it that L is contained in NL? That's almost trivial. Every deterministic Turing machine is also a non-deterministic Turing machine. Why is it that NL is contained in P? Well, you remember that we proved this theorem that if you have a non-deterministic Turing machine that takes space Sn, then you can get rid of non-determinism at the cost of exponentiation. That is, you could make a deterministic Turing machine that takes space 2 to the order Sn and accepts the same language. Now, 2 to the order log n is a polynomial, so you get a polynomial time Turing machine, and this shows that the class NL is contained in the class P. So we have once again a chain of containments. L is contained in NL, which is contained in P. And these are two subclasses of P. Therefore, we know that we can solve all the problems that are in these two classes in practical time. In practical time, we think of P as the class of problems that we can actually solve in practice as opposed to in principle. What we can do is we can apply Savage's theorem to L and NL and try to see what does that give us. So NL is the set of all problems that can be solved in logarithmic space. Now, what if we apply Savage's theorem? Savage's theorem says that we can get rid of non-determinism by squaring the amount of space that we use. So if we are willing to take a quadratic blow up in space, we can get rid of non-determinism. So just applying Savage's theorem, we obtain the following theorem, which says that NL is contained in space log squared n. However, this does not show us that NL is equal to L. So Savage's theorem, which is a very interesting, very powerful theorem, was able to show that P space was equal to NP space, and it was able to solve the non-determinism and determinism question as far as polynomial time is concerned, is not powerful enough to separate L and NL. It does not tell us anything about it. All it says that NL is contained in space log squared n, whereas L is the set of all problems which is equal to space log of n. So Savage's theorem, what it does is it squares log, and we know that log squared n is not order log of n, and therefore the question is not really resolved by Savage's theorem. And once we come to a question which is not resolved by an existing technique, that is considered to be very exciting in computer science and mathematics, because we know that in order to solve such a question, we would have to invent new methods which will give us new insights, and it will force us to think more and come up with techniques which were not known before. To study L and NL, we realize that polynomial time reductions are going to be useless. Thus, what we have to do is we have to define a new reductions. So let's make some definitions. But before we get to the definitions, let's see why is it that polynomial time reductions are not going to be useful. Suppose that you have a problem which is known to be in L. Let's say B is a problem that is known to be in L. And let's say that you can reduce A to B in polynomial time. Now, this reduction immediately gives you an algorithm to solve A. What you can do is reduce A to B in polynomial time and then use the algorithm or use a Turing machine for B to find out whether X was in A or not. So if you're given an input, you can take that input, use the reducibility to compute some Y, and then find out whether Y is in B or not. And this would be a correct algorithm that decides A. However, what is it that you can say about this algorithm? The reducibility took polynomial time, and then solving the problem for B took logarithmic space. So all you'll be able to do is say that A is in polynomial, A is in P. But that's not what we are really after. That's not, here the problem is that the reduction seems to require more resources than the class L itself. And therefore, polynomial time reducibility turns out to be a very wasteful. We end up spending a lot of resource in converting the problem from one to the other. And therefore, the polynomial time reducibility is not the proper reducibility to study this question. We'll come back to this point in this lecture. Let's start with our definition. So we define something called a log space transducer. A log space transducer is going to be a Turing machine with an input tape, a work tape, and output tape. The input tape is read only, the output tape is write only, and the machine on input X of length n is allowed to use order log n cells on the work tape and produce its output. So a log space transducer, what it does is you give it an input X and it computes a function f of x and writes it on the output tape. And in order to do this, it only uses order log n space. So in other words, a sort of intuitive way of thinking about it converts x into f of x by using a constant number of counters. If a program uses a constant number of counters and no more space, well, that's going to be a log space transducer. However, formally, it's required to only use order log n space. Well, in this case, once again, I want to emphasize this, that the input is not counted as the space used by Turing machine. The machine is allowed to read the input over and over again. Only the space on the work tape is counted as space used by the TM. So the transducer only uses space on the workspace. Let us design a log space transducer that on input x computes 1 to the length of x squared. This is very easy. So suppose you give it some string x as input. Then what this log space transducer will do is write down 1, 1, 1, 1, 1, and how many of these ones will it write down? That will be the length of the string that you gave it and the square of that. So for example, if you give it a string of length 5, it will write down 25 ones. If you give it a string of length 20, it will write down 400 ones, and so on. So how can we design a log space transducer for that? It's very easy. What we have to do is now be space efficient. So here is a simple algorithm which is very space efficient. So this algorithm gets an input x and it sets a counter to 0. And every time it reads a character, it increments the counter. So the counter will be kept in a binary, so it will be a binary counter, and after the machine has finished reading the input, it actually has written down the length of this input into a counter. And this counter will use only logarithmic space, because if the string had length n, then n can be written in log of n bits. So only logarithmic space is used, and we know the length of the string, and it's stored in this counter, this variable that we call counter, and this was only incremented. Now this uses two loops. The first loop I goes from 1 to the counter, and the second inner loop j goes from 1 to the counter, and the machine prints 1. So how many ones will it print? Well, this kind of problem you know how to solve already in your analysis of algorithms class. You have an index I going from 1 to counter, j going from 1 to counter. So how many times the inner loop will be executed? That will be executed counter squared number of times, and counter has the length of x stored in it. So it will print 1 to the length of x squared. So it will print as many ones as So if x has n length n, it will print n square once. Or in other words, it will print 1 to the length of x square. We notice that this machine only uses 3 counters. Both these counters will have the maximum value n in them, and therefore they only need to be log n bit counters. The output is clearly n squared bits. So what's interesting here to see is the input is n bits, the output is n squared bits. However, the space used by this Turing machine is only 3 counters. It is log n, order log n bits. So this is a log space transducer. Now, what I claim is that it's very easy to argue that if a log space transducer produces an output f of x, then the length of f of x is going to be less than or equal to length of x to the power k for some constant k. The rough idea about how you can prove this statement is, suppose a log space transducer gets an input of length n. What we want to do is, we want to show that the output cannot be more than n to the k bits for some k. Since the log space transducer only uses logarithmic amount of space, log n amount of space, therefore we know that the number of configurations that this transducer can go into is 2 to the order log of n. That's because that's the total number of configurations that can happen on the work tape of length log n. And this quantity is n to the k. It's a polynomial for some k. And therefore, if a log space transducer takes more time than this, then it's an endless loop. A configuration would be repeated. And since we are claiming that it produces an output and halts, therefore it cannot be going in an endless loop, and thus the length of the output would always be polynomial in the length of the input. Now, let us say that a language A is log space reducible to B if and only if there is a log space transducer that computes a function f of x such that x is in A if and only if f of x is in B. When A is log space reducible to B, we will write that as A is less than or equal to sub L B. So we will use this less than or equal to notation to say that a language A is log space reducible to B. Well, remember the first condition is that if x is in A, then f of x should be in B. If x is not in A, then f of x should not be in B. This means that what you can do is you can take a string in sigma star, apply f to it, and by knowing whether f of x is in B or not, you can tell whether the original string x was in A or not. We've seen reducibilities. This is a very natural property of a reducibility. It leads us to a very natural algorithm. Here, notice that we must be able to compute the reducibility in a tiny amount of space. Tiny meaning logarithmic amount of space. Of course, if you're using logarithmic amount of space, our reducibility will automatically be polynomial time reducibility. But when I say a log space reducibility, I'm actually requiring more. I'm saying not only that it should be computable in polynomial time, but it should be computable in tiny amount of space, logarithmic amount of space. That's a stricter requirement than requiring it to be polynomial time computable, which was our polynomial time reducibility. This is a stricter reducibility. So if A is a log space reducible to B, that immediately implies that A is polynomial time reducible to B. Well, once we have defined this log space reducibility, we would like to show the following theorem. The theorem says that if B is in L and A is reducible to B, then A is also in L. This is a typical theorem. We have proved a similar kind of theorem for the class P. We know that if B is in P and A is polynomial time reducible to B, then A must be in in P also. And here we're saying that the log space reducibility has the same role for the class L that polynomial time reducibility had for the class P. Any problem that's reducible to that's polynomial time reducible to a polynomially solvable problem is itself polynomially solvable. On the other hand, this is saying any problem that is log space reducible to a log space solvable problem itself must be log space solvable. This theorem is not trivial. It's harder than what we have done before. This theorem is harder to prove than its analog, the one that was the polynomial time reducibility analog. That one is just trivial. Reduce A to B, use the algorithm for B, and that's it. Compute how much time it takes, and it turned out to be polynomial. Here we will see that we will need to pull out a trick. So what we will do is start by giving a simple solution to this problem and see why that is wrong, and then work out a correct one. We know that A is log space reducible to B. That's what's given to us. A is log space reducible to B, and that B is in L. We want to show that A is in L. So since A is log space reducible to B, thus there is a log space transducer which we give a name N, which computes a function such that x is in A if and only if f of x is in B. Further, we know that B is in L. So there is a Turing machine M that uses order log n space and accepts B. So we have two facts. The reducibility can be computed in log space, and the membership in B can be checked in log space. Let's put these two facts together and see that we get an algorithm. Let's see whether it's a correct algorithm for finding out if x is in A or not, and how much space does it take. So let's consider the following Turing machine. Suppose it gets an input x. What it does is it applies the log space transducer n and computes y, which is equal to f of x. Now it runs m on y, and if m accepts, it accepts, otherwise it rejects. So this is a very simple two-step algorithm. First, apply the reducibility, then ask the membership question for B. Is it a correct algorithm for A? Is it a Turing machine that accepts A? Well, it is, and that's trivial. If x is in A, f of x is going to be in B, therefore m will accept. Similarly, if x is not in A, f of x is not going to be in B, therefore m will reject, and thus we will be accepting x or rejecting x according to whether it is in A or not. It is a correct algorithm for A. How much space does this algorithm take? Let's look at that. The first step is to compute f of x and write it down. Now notice that f of x can be computed by a log space transducer. So computing f of x takes only order log n space. But f of x, we have to write it down so that m can read it. And writing down f of x can require a lot of space. Thus, this is not a log space Turing machine. We need a new idea. To see that you cannot say that when you write down f of x, you use log space, look at the example transducer that we did. It took an input of length n and produced the output, which was n squared bits. But the auxiliary space that it used was tiny, only order log n, in fact only 3 counters. So our log space transducer, although it uses very little workspace, the output may be huge, the output may be polynomially long. If the output is polynomially long and we try to store the whole output, that means we can only write it on the workspace, and that we are not allowed to use that much space. We are trying to show that A is in L. Therefore, we need a new idea in order which does not write down the whole output f of x, because that's very expensive. We have only logarithmic space to use. The new idea is to use what I call the man-in-the-middle attack. Let us see what the man-in-the-middle attack is. So, let me explain this man-in-the-middle attack by explaining to you a story, an epigraphical story, which is probably not true. but it's very famous, and a lot of things like this happen, or today on the internet, a lot of things like this happen. So the story is about a person who did not know how to play chess, just could barely recognize the chess pieces. And what he did was he challenged his friends that he will play 2 games with 2 grandmasters of chess, and win at least one of them, that he's so good that he can do that. His friends knew that he was not good enough to win against any of them. How could he, play against 2 grandmasters and just win one of these chess games, or at least draw one of these, or draw both of the chess games? Well, so the story goes as follows. What this guy did was he contacted 2 chess masters and started playing with them over mail. And with the first grandmaster, he chose to play the whites, and with the second grandmaster, he chose to play the black. Imagine me playing 2 games. One chessboard is placed here and the other chessboard is placed here. And here I'm playing with whites and here I'm playing with blacks. Now, what I would do is, since I'm playing blacks here, the person here, the grandmaster who's sitting over here, will make the first move. He will move a white piece. And what I do is I'll notice that white piece moving and I'll make the same move on the white over here. Then what would happen is, once I've made this white move, the person who's playing black here will have to respond to my move. So this person plays the black, responds to my move, and here I'm playing black, so I will give exactly the same response by making the move that this person made in black. And then to my black move, the person in the white will respond and I will make the move on this board. So this way I will have 2 chess boards. Now if you see, what's happening is I have become the man in the middle. These 2 chess grandmasters are playing against each other, and I'm just moving pieces, and they don't even know that they're playing against each other, because I'm taking the moves of one grandmaster and taking the responses of the other and just making them play against each other. So since these 2 are grandmasters, one of them will win. If one of them wins, then I'll win that at 1 game at least, and if both of them draw, I would have drawn against both the chess masters. So this kind of idea is called the man in the middle attack. Now, if you think about the man in the middle who's sitting there, he's completely dumb. He just needs to be able to recognize moves and not be very intelligent. And we will use a similar idea to show that if A is log space reducible to B and B is in L, then A must be in L. Well, let's think about what the setting of this problem is. We have an input X. We have a transducer that computes f of x. We have another machine that takes f of x, uses work tape, and tells us whether f of x is in B or not. We want to combine these 2 things without using a lot of space. So the idea is to merge these 2 tapes and use the man in the middle attack, and thus the information that the lower transducer needs will be only given to it on a need-to-know basis by the transducer that's working upstairs. Let's work out the details. Let's observe that the Turing machine M, which is the machine that recognizes B, reads 1 character at a time and then performs 1 step. And what we want to do is we want to simulate this Turing machine M. So if I want to simulate this Turing machine M, it reads something from its read-only tape, it reads something from its work tape, and then it performs a step. But it's reading only 1 symbol from the read-only tape. So we will provide it this 1 symbol on a need-to-know basis. Thus, in order to simulate this Turing machine M, we only need to know what the current symbol under its read tape head is. The storage tape of M would be provided to it, that it would be allowed to use it as an ordinary workspace. So when we compute f of x, we will not give M the entire y, but only give it portions of it or symbols of it on a need-to-know basis. This is the basic idea. Now let's see how this would be done. We can now simulate M as follows. To find out what is the current symbol of Y that is being scanned by M, this symbol would be needed to perform one step of the simulation. What we can do is we can run the transducer N on X to compute that particular symbol and then take one step. So, for every symbol that is needed by the bottom Turing machine M will be recomputed by the above transducer. So let's say M needs to know what the 17th symbol is. Then we will run the transducer N, it will start producing output, and what we'll do is we'll keep discarding the output that's producing by rewriting over it till it writes down the 17th symbol. And once that 17th symbol is written, note that the first 16 symbols were discarded, so they didn't require any space to be stored. Once we know the 17th symbol, we'll provide that to M to do one simulation step. Then the tape head may go to the right. And that means that now M needs the 18th symbol. We'll rerun N, discarding all the symbols till it computes outputs the 18th symbol, and that will be provided to M. Now M may move to the left and it may need the 17th symbol again. Well, 17th symbol was never remembered. So we'll run this transducer completely again, discarding the first 16th symbol, and once we reach the 16th symbol, it will be provided to M to continue its simulation. So the space will be reused over and over again, and the output f of x will never be stored. Only individual bits of it would be computed as required. Thus, if M needs the ith symbol of Y, we can run N on X, and every time it produces an output, a counter will be incremented. We discard the output by erasing it if the counter is less than I. This way the output does not use any space. When the ith symbol is produced, we give it to the machine M, which performs one step of its computation. So this way, the output f of x, y equals f of x, which was using all that space, does not need to be stored. How much is the space requirement here? Well, we need a work tape of the original transducer. We need to have storage for the work tape of M. Both of them require logarithmic work tape. So the total is going to be logarithmic. However, we don't store y. Instead, we use counters to generate the ith bit of y. Thus, the space requirement for the counters is going to be order log of y. So, therefore, by using few extra counters, the space requirement of this new Turing machine is going to be order log n plus order log of y. Now, we already commented that the length of y can be at most n to the k. This, the whole procedure will take logarithmic space. So, this clever simulation, which doesn't write down the output but computes it bit at a time, uses it to do one step of M, is a clever way to show that A actually can be recognized in logarithmic space. Thus, we have proved our theorem. If B is in L and A is log space reducible to B, then A must be in L. Notice that we would not have been able to prove this theorem if we were using polynomial time reducibility. That's because if we were using polynomial time reducibility, then we have no control on how much workspace the transducer will take. It could have taken polynomial amount of space. Of course, it can't take more than that, we know that, but it may have taken polynomial amount of space, and that would have just told us that A is in T space. But that's not what we wanted to prove. We wanted to prove that A is in L. And that's the reason for using this sharper notion of log space reducibility rather than our previous notion of polynomial time reducibility. Thus, log space reducibility is what we need to study the class L and NL. Now let's come to the central question in space complexity. the actual analog of P versus NP in space complexity. We have L, which is log space. We have NL, which is non-deterministic log space. The question is whether these two classes are the same or not. So the question whether L is equal to NL is what we want to study, and this is a major unresolved question in space complexity. Solution to this problem will of course mean instant fame and glory. It turns out that the space complexity question, when we talk about polynomial space and non-deterministic polynomial space, is although interesting, but we can solve it. Savage solved it, and he showed that P space was equal to NP space. But when we come down below inside P and look at the class L and NL, this question becomes extremely interesting, meaningful, and is very difficult. We haven't been able to resolve it yet. This problem is very interesting. Let's see why it is very interesting, and let's contrast this problem with the P versus NP problem. So what I want to do is I want to look at the P versus NP problem, what is known, what do people think about it, and L versus NL problem. P versus NP problem talks about what happens, what is the power of non-determinism when we look at things from polynomial time point of view. NL versus L problem is what is the difference between non-determinism and determinism when we look at things from a logarithmic space point of view. Now let's go and define two other complexity classes which correspond to P and NP. Let's define the class co-NP. This is the set of all languages whose complement is in P. Or what we do is we go into P and we look at all the languages and we collect their complements and put it in this one class, and we call it the class co-NP. Notice that co-NP is not the complement of the class P, or co-P is not the complement of the class P. It is the set of all languages whose complement happens to be in P. Let's define co-NP analogously. We define co-NP to be the set of all languages whose complement is in NP. Now it's very easy to see that P is equal to co-NP. Or in other words, we have a closure property of the class P. The class P is closed under taking complements. If a language L is in P, then its complement must be in P. If a language is in P, then its complement is also going to be in P. And if the complement of a language is in P, then the original language must be in P. The proof of this fact is very simple. If you have a non-deterministic Turing machine and you change its accept states to reject states, then it accepts the complement of the language. Furthermore, it runs in the same amount of time as the original Turing machine did. Thus, for every language L in P, you can take a polynomial time Turing machine, flip its accepting and rejecting states, and you get a polynomial time Turing machine which solves its complement. On the other hand, what about co-NP? What kind of a class is that? Well, it's not obvious at all that co-NP is going to be equal to NP. Because remember, NP is the set of all problems whose membership can be easily verified. Co-NP would be the set of all problems whose non-membership can be easily verified, and they are two different things. Let me explain. Now suppose that I tell you that the set of all three colorable graphs is a problem which is in NP. Well, there is an easy verification algorithm. Namely, if you give me a coloring, I can easily check that the coloring is a proper coloring and it only uses three colors. On the other hand, non-three colorability, the set of all graphs which are not three colorable, there doesn't seem to be a very easy way to verify that a graph is not three colorable. How would I prove to you that a graph is not three colorable? Well, to prove that a graph is three colorable, I merely give the coloring. But to prove that a graph is not three colorable, well, it doesn't seem to be, there's no natural, a simple proof that I can provide to you. In fact, many people conjecture that there are no simple proofs of non-three-colorability of graphs. There are no quickly checkable proofs. And therefore, people widely believe that NP is not equal to co-NP. So, what we do is we know that P is equal to co-P, and we conjecture that NP is not equal to co-NP. Now, the following theorem is easy to see. If co-NP is not equal to NP, then P is not equal to NP. If you think about this, this theorem, this says that the NP not equal to co-NP conjecture is stronger than P not equal to NP conjecture. How would you prove this theorem? Well, you can prove this theorem by looking at the contrapositive statement of this theorem. The contrapositive statement of this would be that if P is equal to NP, then NP must be equal to co-NP. Well, if P is equal to NP, then co-NP is equal to co-P, which is equal to P, which would be then equal to NP. Therefore, since we've proved the contrapositive of this theorem is true, therefore this theorem must be true also. However, this theorem shows us that NP is not equal to co-NP is a stronger conjecture than P not equal to NP, in the sense that if you solve this conjecture, then you will solve the P versus NP problem. One way to resolve the P versus NP conjecture is to show that NP is not equal to co-NP. If we show that NP is not equal to co-NP, we would immediately get as a corollary that P is not equal to NP. So the NP versus co-NP conjecture is much, much stronger than the P versus NP conjecture. On the other hand, if someone were to prove that NP is equal to co-NP, that would be a great, great insight, but not resolve the P versus NP conjecture. So the NP is not equal to co-NP is a much, much stronger conjecture than P is not equal to NP. On the other hand, NP is equal to co-NP is a weaker conjecture than P equals NP. So if you separate NP and co-NP, that separates P and NP. But if you show that NP is equal to co-NP, then you do not necessarily separate P and NP. Well, what we can do is we can play the same game with space complexity. Let's define co-L to be the set of all languages whose complement can be recognized in logarithmic time, and co-NL to be the non-deterministic analog of it, that is the set of all languages whose complement can be recognized in non-deterministic logarithmic time. And now we can look at the similar question that we asked before. Now it's easy to see that L is equal to co-L. Well, that's a one-line argument saying deterministic things are closed under complementation. That's the basic theory, but the idea is that if you have a language which can be recognized in logarithmic space, using logarithmic space, then its complement can be recognized by the same machine if you were to flip the accepting states to rejecting state. However, it's not at all clear if NL is equal to co-NL. So that's because in non-determinism, our definition of acceptance is that one path should accept. By flipping the state, that doesn't give us a Turing machine which accepts the complement of the language. Now, once again, it's easy to see that if co-NL is not equal to NL, then L is not equal to NL. Thus, the NL is not equal to co-NL is a much, much stronger conjecture than the conjecture that L is not equal to NL. Thus, we notice that the kind of theorem that holds for co-NP and NP also holds for co-NL and NL, and it has consequences on L and NL. So one way to resolve the NL versus L conjecture is to show that NL is not equal to co-NL. So the story that I'm telling you so far seems to be a repeat of what we know about P and NP and what people have conjectured about P and NP. It's widely conjectured that NP is not equal to co-NP. But when we study L and NL, there's a twist in the tale. The twist is that we can prove the following wonderful theorem. What we will prove in the next lecture is that NL is equal to co-NL. This is a major result in space complexity. The fact that non-deterministic logarithmic space is closed under complementation. This is a result of its own kind, where it says that there is a non-deterministic complexity class which is closed under complementation, and not only just a non-deterministic complexity class, but an extremely interesting non-deterministic complexity class that is closed under complementation. Well, what does this mean? This means that by studying NL and co-NL, we will not be able to resolve the L versus NL question. That question remains still widely open. We have no idea how to solve this question. So in the next lecture, what we would do is we would see how to prove that non-deterministic log space is closed under complementation. And once again, the way we will do it is via some kind of a theory of completeness. We will start with looking at a problem, a very natural problem. We'll show that it is NL complete. And then what we'll do is we'll show that the complement of that problem is also in NL. And as a consequence, we'll find out that NL is equal to co-NL. I'll see you in the next lecture. Thank you and goodbye.